This is a lesson about slope fields. So let's start off with an example differential equation. dy by dx equals 2x. How do we solve this differential equation? It's already set up explicit in terms of y, or there's no y's in it, so we can just integrate both sides in terms of dx, right? And we know the integral of dy by dx is just the original function, so y, and the integral of 2x is just going to be 1/2 x squared. Oh, and there's that 2 in front, right? Let's assume I pulled that 2 out of that integral plus c. So there we go. If we simplify it, obviously these 2's will cancel out, and we just get x squared plus c. So this is the general solution to the differential equation. Now we're asked to find 3 unique solutions to the differential equation. So let's start off with the first one. If we plug in 0, 0 as a point, we're going to get 0 equals 0 squared plus c. So clearly c is just equal to 0, so our differential equation becomes y equals x squared. If we plug in f at 0 is 1, we're going to get 1 equals 0 squared plus c, so c is just 1. So that's, y equals x squared plus 1. And then lastly, if we plug in -2, you can see where this is going. It's essentially just shifting it down. So the differential equation is going to be y equals x squared minus 2, right? Or the solution to the differential equation is going to be that. So let's just sketch these 3 graphs. I'm going to sketch them very roughly. So the first one here just looks like that. The second one is just shifted up. We'll call this the red one here. It's going to be shifted up by 1. And it's going to look like that. And then the last one is shifted down by 2, so it's going to look something like that. So we'll call this the green function. Okay, so we have 3 functions. Now, you notice a pattern, right? Essentially, when we're changing c in this case, or our initial condition, we're just moving it up and down. This won't always be the case, but it is here. So the question I have for you is, can we represent this general solution? We've represented a bunch of specific solutions or unique solutions. Can we represent this general solution? And that's what we do. When we do that, we use what's called a slope field. And it basically summarizes all the possible solutions to a differential equation. Because we can have more. We can have more like that, like that, like that. We essentially have an infinite number of parabolas that look like that. So slope fields are a way to summarize all those different solutions. So how can we create a slope field? This is a differential equation here. Looks pretty simple, dy by dx equals x plus y. But if we try to use our separation of variables technique, you'll notice you actually can't separate the variables. It's impossible, because if we multiply both sides by dx, we're going to end up with dx's times dy, which we don't want. We want to be able to separate the variables. We cannot do that here. So we're going to need to use a slope field to get a better understanding of what this differential equation is. So essentially what we want to do is we want to find what the slope of the function is at any point, x, or any coordinate, I should say, x or y coordinate. So we're going to do this by summarizing it in a table. So let's pick a coordinate, x, y, and then what is the slope at that coordinate? So let's just start off with 0, 0. What's the slope of the function at 0, 0? And if you look at it, 0, 0 is just going to be 0, right? X plus y is just going to be 0. Okay, so the slope is 0 here. And what we're going to do at this point is we're going to represent the slope with a tiny little horizontal line like that. Okay, so let's move on. Let's try 1, 0. What's going to be the slope at 1, 0? Well, if we look at our differential equation, it's just going to be 1 plus 0, which is 1. So the slope here is going to be 1. So we can represent it as a little line like that. And we can keep going. So at 2, 0, the slope is going to be 2 plus 0 is just 2. So the slope is going to be even steeper at that point. And we can keep going. You'll notice here, the slope is just going to get steeper and steeper, right? That's sort of the pattern. Okay, so that's going in the x direction. Let's go in the y direction now. So let's just choose the point 0, 1. The slope of that is just going to be 1 because it's 0 plus 1. So at 0, 1, we're going to have a slope of 1 that looks like that. And if we choose the point 0, 2, what's going to be the slope at that point? It's going to be 2, right? 0 plus 2. So it's going to be steeper. And if we choose 0, 3, it's going to get even steeper and steeper and steeper. So essentially, we just have steeper lines there. So you can sort of see the pattern. We can also go in the negative direction. So what happens to the slope in the negative direction? You can sort of figure out, okay, so if we, for example, do negative 1, 0, the slope there is going to be negative 1, right? So it's going to look like that. And it's going to get steeper and steeper and steeper in the negative direction because it's just going to be bigger and bigger negative numbers. And then we can do the same thing in the y. In the y-axis, we're going to get negative 1, negative 2, negative 3, negative 4, negative 5 as those slopes. What then we can start to do is we can start to sort of fill in the blanks here. So let's choose point 1, 1, for example. The slope is just 1 plus 1, which is 2. So that's going to be a pretty steep line. And as we continue to go across here, as we continue to add x values, it's going to get steeper and steeper. So steep, 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 really, really steep there. And same thing happens when we go up. We're going to get steeper and steeper and steeper. Essentially, we basically have like almost vertical lines as we get to this point here. All right, so I'm just going to fill those in. Right, super steep lines. Going down here, going below the axis here, so at point 1, negative 1, that's going to have a slope of, well, if we plug it into our thing, 1 and negative 1, slope of 0. So we're actually going to have another slope of 0 here. And if you think about it, when we go to 2, negative 2 here, we're also going to have a slope of 0, 0, 0, 0, because those are going to cancel out. And the same thing will happen on the negative side. These will all have a slope of 0, right, because negative 5 and 5 are going to cancel out. And then we can sort of fill in between again. As we continue, like this direction, for example, adding them, we can continue to get steeper and steeper and steeper. So we're going to have a slope of 1, 2, 3, 4. And going the other way, it's going to get steeper in the negative direction. Okay? So this is getting a bit messy. This would be a slope of negative 1. But I think you get the idea. So, and again, we're going to have a slope of 1 here, slope of, there we go. It's going to get steeper and steeper like that. Slope of 1, it's going to get steeper and steeper. Slope of 1, it's going to get steeper, etc. Slope of 1. Okay. All right. So we've created sort of half this slope field right here. You can continue going. I won't often get you to do one that's this intricate. Usually you only have to fill in a few spots. But you can start to see that this actually shows us the direction the function is going to go. So you can sort of see paths if you sort of follow these lines, and these paths represent solutions to the potential problem. And it depends on where you start on the function. So if you start here, it's sort of directing you upwards. The slope fields are directing you upwards. If you start here, it's directing you in this direction. If you start here, it's sort of directing you down on an angle, right? If you start here, it's directing you downwards. So the slope field gives you sort of the direction that the solution is going to go in. So even if we can't actually solve this using separation of variables, we can get an idea of what this function is actually going to look like. I'm actually just going to fill in a few more of these spots so we can see what this thing looks like here. These will be positive 1. These will be steeper. These will be very steep negative, very steep negative, getting steeper. I have a good sense of what these things are going to look like because I've done these before, clearly. So it might take a little bit of practice. You might need to plug in some more points to see what the slope is, but that's basically what that slope field should look like once you're done with it. Something like that. So sort of look at the patterns. Look at which direction the function is going to go. It follows these slopes because remember, these represent the slope of the original function at any point. So it's asking us in this question to sketch the solution to the equation when f at 0 is 1. So basically this is saying where you're at the y-intercept, if you're starting the function here, what's the function going to look like? The original function, the solution to this differential equation. And if you follow the slope lines, the slope field lines, it sort of looks like it's guiding you upwards here. And on this side, it's sort of guiding you backwards here like that. So that's what we would actually expect the solution to look like. It sort of looks like a rational function with an asymptote. And that's what it actually might be. But we don't know that for sure. So that's what the solution, we'll call that the red solution, when f at 0 is 1. What if we start at a different point? What if we start at the origin right here? What's that going to look like? Well, if you sort of follow the slope field lines, they sort of go up like that, right? And if you follow them backwards, it sort of looks like it's going to follow this path here. So it looks very similar to the first one. So we'll call that the green solution. And then if we start at -2, we're starting down here. What's that path going to look like? If we sort of follow these slope lines, they're sort of directing us downwards. And in this case, they're sort of directing us up asymptotically. So that's what that one would look like. So you notice there's actually some different shapes here. And that's why differential equations are so complicated, because depending on where you're starting, or depending on what your initial conditions are, the shape of the answer can actually be very different. Question D is asking us, if we have the initial conditions, f at 0 is 2, so this point up here in the black, if we have that as our initial conditions, and x is greater than 0, what are the possible solutions to this equation? Well, again, the slope field lines are directing us sort of upwards, right? And because they're directing us upwards, it's not like we're going to end up coming back down at some point. The field lines get steeper and steeper as we go. So essentially it's asking us, what's the range of values for a possible solution along this line? Or essentially, what's the range of this graph, right? What are the possible y values of this graph? So the answer here is that clearly it has to be greater than 2, right? Because it's going upwards. And that's the answer to this. Basically, the answer is that x has to be greater or equal to 2. Equal to because we know we start at 2, right? So that's the solution to this equation, right? Well, that's all the possible solutions to this equation when we have the initial conditions. If we had the initial conditions of -2, for instance, we would say that all the solutions possible are less than -2. The last question asks us, when f at 0 equals 0, what's the limit as the function goes to infinity? And we already plotted that. F at 0, 0 is the green one, right? And if the green one, as it sort of goes to the right, as it approaches infinity, the graph is going up. So what does that tell us about the end behavior of the function? Well, it tells us that the end behavior of the function is going to infinity. So that's the answer. X approaches infinity, or the limit is just equal to infinity, positive infinity. If we had chosen a different starting value, like -2 here, our answer would be different. Our limit as x goes to infinity would be negative infinity, right? Because it goes downwards. So there you go. There's your introduction to slope fields.